Okay, so we're recording, and here's where we left off. So we want to talk about some special cases of the chain rule. Just a quick reminder, though, let's talk about what the chain rule was itself. And here's the idea. Big idea is that if you compose two multivariable functions, the composition is a multivariable function, and furthermore, if you think of what the derivatives do, and again, just break it, no details, right? But just break it down to fundamentally, what do derivatives do? Derivatives are multiplicative factors. They're matrices in this case, right? But they're multiplicative factors. So if you want to know altogether what is the total multiplicative factor that takes you from the original inputs to the eventual outputs, right? What is that total multiplicative factor? Well, it's it's the product of the two kind of elemental multiplicative factors. That's the big idea, right? And so again, ultimately, I mean, if you look at it just this way, it's pretty believable, I like to think. And so there we go. And reminder, that means that we have this statement about how derivative matrices multiply when you compose functions. Okay, we did an example last time, and that leaves us to where we are now. Okay, so let's think about this first special case. The first special case is where our original inputs, keep in mind we have a composition of two functions, so there's really kind of three different spaces. So I'm going to refer to these as the original inputs, one-dimensional. So it turns out something really nice happens there. So a couple of nice things in particular. If I look at this function, now I have a bunch of output variables, not a function of a bunch of inputs, but a bunch of outputs are functions of one input. And that gives me two really nice interpretations. First interpretation, there's only one input. That means that that derivative matrix has only one column. The second nice interpretation I can make is that I can think of this original function, the first acting function, I can think of it as, in fact, a parametric curve in Rn. That's what a parametric curve is, position as a function of a single parameter. So, in fact, then, this is, wrong color, this is just the velocity vector of the parametric curve in Rn. Now, likewise, I can look at the composition, right? The composition is like this. And again, same series of observations. There's only one input. That means that the derivative matrix of the composition has only one column. Furthermore, because there's only one input, the composition is actually giving you a parametric curve in Rm, which means that this output derivative matrix, as we discussed last time, is just the velocity vector of that parametric curve. So we can kind of, again, reinterpret all of this, these points in mind. This is a velocity vector there. Let's see here. I'm going to use blue this time. This is a velocity vector there. Right? And so we can interpret the chain rule in this case. Keep in mind, this is what the chain rule is saying. The chain rule, interpreted in this case, is telling us that the derivative of this function, the derivative of f, is the factor you multiply by input velocity to get output velocity. Now, we already knew that, right? But it is kind of cool that you might say that this, what I consider to be one of our fundamental interpretations of what derivative matrices do, what derivatives do in general, is kind of recovered in this special case of the chain rule. Okay, so kind of cool. So now this example is a little silly, but I guess it's appropriate to go ahead and do this here. I say it's a little silly because this is an example of something we already knew how to do. We already knew that derivative matrices turn input velocities into output velocities. And all this question asks is, given an input velocity, what's the corresponding output velocity? right? And you can see that coming to life down here. I take the derivative matrix, which, yes, I have to take various partials and plug in the point in question and put that in the chain rule where it goes. Okay, sure, tedious little, compute, etc. But the derivative matrix is what I'm multiplying by the input velocity. Derivative matrix computes to that to compute the output velocity there. So again, this could just as well have been an example in section 2.3 instead of section 2.5. It's really just interpreting the derivative matrix. Okay, but again, in this special context, I can reinterpret this as an example about the chain rule. All right, how we doing? Everybody buy it? All right, the next special case, and this one's this is barely worthy of mention, but I guess it's got to be mentioned. We just talked about what happens in the special case where you have one original input variable, right? And now we're going to consider the further special case that in fact there is one eventual output variable. And well, if there is one eventual output variable, then the DF matrix has one row. Remember, outputs correspond to rows of the derivative matrix. Okay, and then we've made this observation before that when you have a matrix that is a single row and you are multiplying by a vector, you can reinterpret this, as I have it written here, is a matrix vector product. Okay, right, sure, right, fine. But morally, that's a vector dot product. I mean, it's the same exact arithmetic if you write down which elements get multiplied by which elements and how do you add. It's the exact same stuff, right? So again, not that much happened here. We just kind of recover again old news that in the real valued case, dot product with the gradient vector can be thought of as the derivative. Dot product with the gradient vector is the thing that you do to input velocities to get output velocities. So again, we've already made that observation, right? I just thought it was worth noting that this too is a special case of the chain rule. Okay. So another example, which I'm going to let y'all read. This is very, very readable. It's exactly the same as the previous example structurally, except that now when it comes time to write down the chain rule, I'm doing so with gradients, dot product with the gradient, just as we previously discussed, instead of writing as a derivative matrix. But morally the same. We have an input velocity that's given, and the question is to determine the output velocity, how fast is the temperature changing. And again, you can punch that up. Color problem. Eraser. There we go. You can compute that again by doing dot product with the gradient vector, and of course you got to compute the gradient from the original function, partial derivatives, plugging in the point, yawn. Okay, make sure to look through those details, make sure you're good with that. Okay, new point of view. This is very nice, very useful in lots of situations, surprisingly often. Now, I want to emphasize, I think this is important. I think it's valuable to have this be your cornerstone point of view on the chain rule. I think it's very powerful to think of the multivariable chain rule as a statement about compositions of multivariable functions that results in a statement about derivative matrices multiplying, right? It's crisp. It is an easy picture to draw. It's ultimately the simplest point of view. If you get right down to it, if you've digested the idea of derivatives of multivariable functions being matrices that turn input velocities into output velocities, right? If you've really digested that, this is the simplest point of view. on the chain rule. So that said, in certain special cases, it can be very convenient to think about this different point of view. So here we go. We have a couple of multivariable functions. Here's a multivariable function f. Here's another one, g. You're going to notice that what comes out of f is what goes in to g. Right? So I'm composing, right? Implicitly, I'm composing these two functions. And I can think about, the overall composition function, which takes x's as the original inputs and gives z's as the eventual outputs. Right? So I just wanted to give names to all the variables so I could write down the matrix form of the chain rule, and here it is, matrix form of the chain rule. Notice that the df matrix, from this function f, the one that acts first, very importantly, annoyingly, but importantly, the one that acts first is on the right. Gotta be real careful about that. It's so easy to accidentally get these backwards. I've made that mistake in a careless moment in the past. It cost me quite a bit. But anyway, be very careful about that. The one that acts when you're talking about matrix multiplications, the one that acts first is on the right. Okay, second function, g, right? Its partials assembled to make its derivative matrix is on the left. And then looking at the composition, again, you multiply these, and that gives the derivatives of the composition. What you get when you plug the original outputs into the subsequent inputs, and that's this derivative matrix right there. So this is all set up. I haven't done anything yet. Just writing down the chain rule sort of by coordinates, if you will. Okay, so let's just address the straightforward question. Suppose that I don't need to know the entire derivative matrix. Suppose, this is very often the case, all I really need is one particular element. That happens a lot. Well, if you only need the one particular element, if you think about it, there's no point in computing the entire matrix if you only need just that one particular element. And computing that one particular element, well, it's an element of a product matrix. So I can just identify what row it's in and look at the corresponding row of the left matrix, and I can identify what column it's in and look at the corresponding column of the right matrix, and we have rules for how to compute an element of a product. You compute that element of a product by dotting, like so. Everybody remembers all that? All right, so you get this really nice, you get this much more, it depends on how you look at it, but arguably more compact formula. What's nice about this is there's no matrix algebra sort of concealed by this formula. This is straight up partial derivatives, which are easy to compute, and four-function arithmetic, namely multiplying and adding. A pretty simple formula in that sense. Okay. Everybody good so far? Now, I have to give you all a warning on one thing. There is a temptation. I've seen this happen a lot of times, and this is really, really wrong, and not in a forgivable kind of way. This is actually a dramatic error that's really bad. A lot of students will look at just this right here and think, hey, I don't need the rest of those terms, because looking only at this term, I feel like that cancels with that, and then what I get as a result is partial zi, partial xj, which is what I wanted. Everybody see the temptation there? This is a dangerous landmine. This is absolute garbage. Superficially, it looks good. That's superficial and meaningless. And so please do not step on this landmine. Now let me try to persuade you that this actually literally does not work. And in particular, I want to address the reasoning, such as it is, that I pretended to make here. And here's the problem with the reasoning. The problem with the reasoning is that, believe it or not, this and this are not the same thing. It's very unfortunate. The notation for partial derivatives has a major problem, this Leibniz notation. The Leibniz notation makes it look like this is a fraction. In particular, it makes it look like it's a fraction representing a ratio of two independently well-defined things, and they are not. It's just not. So, in particular, let's think about this partial y1, right? What does this represent? Well, this represents how much y1 changes in a certain scenario. The scenario in which this represents how much y1 is changing is a scenario in which, again, keeping in mind these are partials, all the other y's are constant. That's how partial derivatives work. That's what this represents. It represents, again, a scenario where all the other y variables are constant. Now let's think about what this partial y1 represents. This is part of what I claim is a completely different and inconsistent scenario. If you think about it, this is a partial with respect to xj. That means that I'm holding all of the other x variables constant, but I am, as I do this, changing xj. And if you are changing one of the x variables, you are absolutely also, as far as you know, changing the y variables. So here the y variables are not constant. Point being, these are not the same thing. These are representing what's happening to y1 in completely incompatible stories. Right? You cannot take a novel written, by one author that has a character named Steve, and then take some other novel written by a totally different author, totally different story. Well, but there's a character named Steve in this story as well, and then talk about the single Steve, right? Totally different people. Complete nonsense. Everybody see what I'm talking about there? Okay. So make sure to understand this nonsense where you cancel like that and then conclude that this is true is garbage. Again, superficially it looks good, but when you actually dig down and understand what these things actually are, what they're actually representing, it's completely meaningless. It's garbage, right? Again, keep in mind, what is this class about? Is this class about answers? No. Is this class about, what might we call superficially forgivable inadvertent mistakes? No, of course not. This class is about ideas, right? Got to understand what's really going on here. On the exams, I'm going to try to get into your head and see what you really understand about what we're doing here. And so this is evidence of, at best, a very superficial understanding of the ideas. And it's not good, and it's not how you get points. Okay, so that's a long soapbox speech about this issue, but again, the more I talk about this problem, the less I see it on exams, and the less I have to count off on exams, and I hate counting off. So please don't let that be you. Pause. Questions? Everybody on board? Okay, so how am I going to remember this equation? Am I going to have to write down the matrix form every time before I write this down? It seems like a lot of trouble to go to. By the way, keep in mind what I wrote down here. Yeah, I suppose you could literally memorize this formula, but this assumes that the variables are set up exactly as we have up here at the top of the page, and that's just not going to be the case most of the time. Most of the time, your inputs will not be called x1 through xn, and your intermediate variables will not necessarily be called y1 through ym, etc. Right? So much better to have a more efficient way to sort of generate this equation as you need it as you go along. So let me show you what I think is a lovely point of view on where this comes from. And this is the idea of looking at how changes propagate along paths. I think this is a really nice point of view. So let's think about this scenario where I'm interested in the partial of zi with respect to xj. Here's xj. Here's zi. Those are the things that I'm interested in ultimately. Partial derivative means that all of this stays constant. All of this stays constant. So what happens? Right? If I start changing xj, what happens? And there's actually a bunch of things that happen. The first thing I want to point out about what happens is that as xj changes, that will cause y1 to change. And I can tell you exactly how much. Right? What is the factor by which changes in xj will cause changes in y1 when all the other x's are being held constant? Well, it's the partial derivative. It's this partial derivative right there. Right? And then another thing happens, and that is that as a result of y1 changing, the changing of y1 will contribute to the changing of zi. And this partial derivative keeps track of that contribution. Now let's be a little bit careful here. This does say partial derivative. That therefore means that I'm supposed to hold all these variables constant. They're not constant. But we will deal with how these other y variables are changing in just a minute. For the moment, I'm just thinking about how xj's changes propagate along this first path, this sort of top path here. And as the change propagates along this path, the changes in y1 only are what we're interested in. Okay, so another way to say this then is that this path, right, creates this term. This path, by the way, corresponding to what you might call this intermediate variable, y1. What you might call the y1 path along which changes can propagate, right? Creates what you might call the y1 term. In fact, let me highlight this. The y1 term, you might call it, in our chain rule. And then et cetera, et cetera. And you can do this for various other paths. There's a y2. Oh, I wanted to change the color. There is the y2 path and the y3 path, et cetera, and those give you more and more terms. And then eventually, let's look at the last one. There is the ym path. And notice that gives us what you might call the ym term. So I think this is a lovely point of view for every intermediate variable, for every variable kind of in the middle, if you will. The output from the first function, those are the input to the second function. For every intermediate variable, there's a path, and for every path, there's a term. And the structure of the terms is always the same. By the way, notice that it's always zi up here and xj down here. So the pattern is very consistent. When you're composing two multivariable functions, partial derivatives propagate along paths. Paths contribute terms that correspond to intermediate variables. Very convenient, very satisfying, I think. From a certain point of view, I wouldn't call this rigorous, right? But I think it's very satisfying and persuasive. Okay, so let's see an example of this in action. Here is a composition of functions, and now you'll notice, again, what comes out of the first function is what's going in to the second function. So I'm composing these two functions as I have it written. And let's think about how to compute this. Oh, whoopsie. Let's Let's think how to compute this partial derivative right here. This question, by the way, this is how the question comes to you. You will notice that the question comes to you just with algebra. Right? It's just here's a bunch of algebra. Compute this other algebra. I have a very strongly felt bit of advice for how you should address questions like this, and the very first thing you should do in a question where you see that there is a composition happening and you're asked to compute a partial derivative, draw the diagram. So important, so useful, so easy to get lost if you don't. Right? Really, really important. Please draw the diagram. Cannot emphasize that enough. So let's think about what the corresponding diagram is here. Let's see here. The function f takes x1, x2, x3 as the inputs, and y1, y2 are my outputs. So boom, there you go. Let's write that down. This is sort of the left half of our diagram. And now let's think about the second acting function. G takes y1 and y2 as the inputs and gives z1, z2, z3 as the outputs. Okay, cool. There you go. Second half of our diagram. So now what we have is what I like to call a little road map that keeps track of what leads to what. And when I start thinking in terms of how changes propagate along this diagram, I've got my little road map. And all I have to do is kind of follow the road map. So notice we've been asked to compute the partial of, let me use colors better here. Been asked to compute the partial of z2. That's my second output variable. Oh, yeah, question.
Question about the diagram?
Yeah.
Doesn't z2 equal y1 cubed?
Z2 is y1 cubed, yes.
Okay, so then why does the diagram show y2 leading to z2?
Because you can have something be a function of other variables even if those other variables don't contribute anything, right? So I can talk about the multivariable function f of x comma y comma z, whose formula is 6.
Okay, so we're just assuming y2 is an implicit 0 or whatever.
It is literally, if I were to define z2 as a coordinate function that comes out of, it's a coordinate function of g, it is literally a function of two variables. Okay. It is one of the input variables. So the point is, it doesn't have to contribute, it's just that it's allowed to contribute. Does that make sense? It doesn't have to show up in the formula.
Okay, thanks.
Yeah. Okay, I hope that's satisfying. Yeah. It's a little weird, but if you look back at the definition of a function, think about so a function has a domain and a target and a rule of assignment, right? It's not defined in terms of formulas and stuff making a difference, right? It's just literally if you have a domain and a target. And what I have here, this function g, implicitly, this function g is defined on R2. That's the domain, full stop. It doesn't matter what the formulas look like. I hope, okay, good, yeah. Okay, so Z2 is what I've been asked to compute the partial of. There it is in my diagram. X2 is what I'm taking the partial with respect to. There's X2 in my diagram. Now, having drawn this diagram, having identified where these variables are in my diagram, I don't have to think about derivative matrices. I don't have to sort of multiply, think about the structure of matrix multiplication. No, I can just think about paths. And so, you want to compute that partial. Cool. There's what you might call the y1 path, and so I write down a y1 term. That's where the y1 goes. Z2, of course, goes there. X2, of course, goes there, just like previously discussed. So there's the y1 term, and then here's the y2 path, and here's the y2 term. And so, bam, there's my chain rule. No matrices necessary. Just go, boom, right to it, write it down. Algebra produces a diagram, produces a formula. Everybody good? Okay. And then, sure, you have to compute various partials. And again, y'all are proficient, I hope, at this point of looking at these formulas. Let me just point to one in particular. Let's see here. Where did I get that the partial of z2 with respect to y1 is that? Well, don't forget that z2 is, it says right here, that right there. Right? And so you take the partial with respect to y1 of z2, and you get that. Is everybody happy? Et cetera, et cetera. Okay, couple of warnings. A couple of more landmines that I just want to make sure nobody steps on. These are easy landmines to step on in various circumstances. Lots of students crash and burn because of these dangers. It is super easy to inadvertently confuse your variables. And let me show you what I mean by that. I'm going to start with a single variable example. Let's think about this question right here. This question gives me a couple of functions. F, perfectly well-defined function. G, no problem. Perfectly well-defined function. Not a thing wrong with how I've written F or G. The question comes up of how to compute the derivative of the composition. Perfectly reasonable question. They gave us two functions. I'm allowed to compose them. I'm allowed to talk about the derivative. Nothing wrong with any of this. Okay. And then, you come back to the chain rule. Here, I'm just going to go back to our single variable chain rule. Wow, that's way far back here. Here's our single variable chain rule. And, notation, Leibniz, blah, blah. But look, compositions turn into products. I'm just going to compute the individual derivatives and multiply them, right? It kind of seems like this is what this says. So let's naively follow that rule. And I can directly compute G prime out of this formula. G prime is that. And I can directly compute F prime out of that formula. It would seem F prime is that. And then I get what we now, of course, I'm sure you noticed, is the wrong answer. So what went wrong? Okay, what went wrong is I played fast and loose with the chain rule. That's not how the chain rule works. Here's the Newton notation for the chain rule. And yes, derivatives do multiply, but you have to be careful to evaluate at the appropriate places. And I'm sure y'all recall G prime has to be evaluated not at x, but at f of x. And so with that in mind, I should have plugged an x squared into the G prime, which of course is 3 times the square of whatever you plug into it. And that then correctly gives you the right answer. But I'd like to point out that even this solution here, which is, I guess, valid, still kind of unseemly. There's something really uncomfortable about this. This question, this solution as I have it written, is kind of keeping the notation that we were given. And I claim you can't keep that note. It's uncomfortable. I hesitate to say wrong. It's really awkward. It's really dangerous how this is written. And the reason why is, after that was written down, somebody said, hey, by the way, we're going to compose those. Compose means what comes out of the first one is going to be what goes in to the second one. The way this is written down, it kind of looks like we're saying x is equal to x squared. And it's obviously not. That's not good, right? This is very confusing, highly undesirable, and I encourage that you should never do this. So here's what I propose instead, and this is not a difficult solution. This is just, let's just avoid the problem. Let's recognize, because this was written down, because we decided to compose, and because what comes out of F is x squared, let's just recognize that I really can't call that x anymore. It's not x. The thing that goes into g is got to be called something else because whatever it is, it's going to be x squared. Can't call it x. And so this is easily dealt with. No problem. Just take your formula for the second function, realize that I should call its input something else, and rewrite that function accordingly. Don't think of g as g of x equals x cubed. Think of g as g of y equals y cubed. That's perfectly legal. After all, x up here is just a dummy variable. I could say g of Bob equals Bob cubed. It's just a placeholder, right? It's not an actual thing. It's just a placeholder. I could use any placeholder I want. And here I've decided to use a placeholder that avoids the confusion of variables. So now there is no problem. There is no confusion of variables. I have, let's see here, the thing that comes out of f is supposed to be the same as the thing that goes in to g. Cool. X squared is supposed to be called y now. All good. There's no confusion. There's no sort of double roll for x, right? It's no problem. Does everybody see how this is ultimately actually very natural? This avoids a very, very nasty ugliness. Just rename your variables appropriately. And now, what's beautiful about this is now you can play as fast and loose as you want to with the chain rule. I could be totally careless about writing down the chain rule as, the derivative of composition's the product of the derivatives, do whatever. I'm not indicating what's evaluated where. It's all going to automatically be taken care of for us by the notation. Derivative of g, 3y squared, derivative of f is 2x. You multiply that out, you get this, and we're just not quite done yet. This composition, of course, is a function of x. If you're asked to compute the derivative of a function of x, your answer should probably be written in terms of x. Okay, fine. So the last little bit is to recognize that this y that is in our answer, our temporary answer, that y, being the input to g, is the output from f. And so just plug that into there. And the correct answer comes out, and everybody's happy. Everybody cool with that? So I think this is a much better way to think about the single variable chain rule sort of confusion of variables problem. Now, all that said, it's just not a Calc 1 class, right? But why did I spend time talking about that? And that's so that you would be content, I hope, with my suggestion that the exact same point applies in the multivariable case. And it's a lot less obvious in the multivariable case. When you're doing the multivariable case, you got matrices and partials, and you can get a little confused. There's a lot going on. There's bigger expressions and a little scarier looking, perhaps. Excuse me. And it's easy to lose sight of this point. And it's surprisingly easy to make this mistake in the multivariable case. Silly though that seems, and again, I presume most of y'all rolled your eyes when you saw this. What a silly mistake, right? But again, a lot sneakier in the multivariable context. So, same solution. We have a couple of functions given to us. Nothing wrong with either one of these functions. Those variables x and y are, after all, just dummy variables. And until I say I'm going to compose them, there's nothing wrong with writing them in terms of the same dummy variables. Perfectly legal, right? It is our job, as people answering the question, to recognize, oh yeah, okay, sure, but now you're saying you want to compose them, and when you compose them, what comes out of the one function, I can't call those the same x and y that went into that function. It's just problem confusion of variables. So just recognize that that's the case. Decide you want to call them something else. I don't know, U and V, whatever, S and T. Whatever, suit yourself. And once you've decided what you're going to call them, then just recognize that that means you have to rewrite that second function. This says, right here for me, I need to rewrite G in terms of not X and Y, but in terms of U and V. And so this turns into that. Now, emphasize, I didn't do anything there, right? That's the same exact function G. Same exact function G. Just written in terms of a different dummy variable. Kind of means nothing. And having done that, again, go crazy. Play fast and loose. Don't worry about you got to evaluate this, where, etc. We just take the appropriate partials to compute the derivative matrices. You multiply to get the composition. And the work of keeping track of what you plug in is done for you by your notational choices. And so in particular, let's see here, I've got, in my answer here, I've got a V right there. Oh gosh, what am I going to do with that V? Well, V, it says right here, V is my second my second input from the G function. That means it is the second output from the F function. That means that V is x squared minus y squared. And so I plug that in. Does that make sense to everybody? Likewise for you. Okay, so it's a silly little problem, but again, surprisingly dangerous. A lot of people step on that landmine. Don't let that be you. Always think about, and again, one of the nice advantages of drawing your diagram is it forces you to acknowledge whether you have or have not written down a bunch of confusion of variables nonsense. So yet another reason to always draw your diagram. Okay. All right, now there's a whole larger category of what I'm going to call related problems, and these are very confusing. And you can avoid all of that confusion by just being careful and following the rules. It's surprisingly important. Now, first point I'm going to make is that we start off by composing functions. I mean, if you look back at the very first thing we said about the chain rule, I was assuming that we were composing multivariable functions. Composing is a big word. When you're composing functions, what comes out of the first function has to be exactly what then goes into the second function. You can't, I think I'm going to introduce a couple extra variables in here, or stuff like that. So you got to make sure that when you try to apply the chain rule, that what you're writing down is actually a composition of functions. Now, this diagram right here is, in fact, representative of a composition of functions. And you can see it right in the diagram. Here's the first function, and what comes out of that first function is exactly what goes in to my second function. No issue. So this diagram is representative of, let's say this diagram did come out of where our theorem came from, namely a composition of functions. So, cool. Let's look at this diagram right here. This did not. This diagram, this is just a made-up diagram. This did not come out of a composition of functions. What functions are they, presumably, that are being composed here? And is it true that what comes out of the first is exactly what's going into the second? I say no, it's not. And let me show you the kind of nonsense that you can run into if you do something like this. If you find yourself in this sort of a situation, let's think about what this might mean. And the answer is going to basically be that this doesn't really mean anything anymore. So let's think about it. Partial of z1 with respect to x1. There's z1. What's it a function of? Oh, it's kind of a function, would appear, a function of those three variables. Those are the three things that contribute to changing it. So I should say z1, it would appear, has got to be a function of at least these three variables. So if I say I want to take a partial of z1 with respect to x1, that means that x1 is supposed to remain a variable, and these other inputs are supposed to therefore stay constant. And that's garbage. You're telling me I'm supposed to change x1, but y1's not going to change. But y1's a function of x1. This is a completely nonsensical scenario. It's garbage. So we've got a major problem. If you have a situation like this, this does not represent a composition of functions. We have no chain rule to address that. Everybody see the problem? And if you try to, well, I'm just going to kind of write some stuff down that seems to be like the closest best guess, well, that's a bunch of nonsense. You might get lucky. You might get lucky. Very often you would get lucky. Again, not the point. It's nonsensical reasoning. Right? So let me show you how to fix this. It's ultimately not that big a deal. I'm going to start off by recognizing that these equations here kind of suggest this diagram. In particular, look at this. y1 is a function of x1 and x2. Cool. And y2 is a function of x1 and x2. Okay, cool. And let's see, color choices. z1 is a function of those, just like I have in the diagram, right? And then this is a function of those. I mean, this is a kind of algebra that can come at you that you might want to represent with a diagram like this. And then you write the diagram and you realize this is a mess. Okay. So we fix it as follows. Roughly speaking, I'm going to look at this diagram and I'm going to say, look, if there were another variable there that kind of went along with these, I'd be all set. Because look at that, then I would have those purple variables, one of them hypothetical that doesn't exist yet, right? But if there were a purple variable right there, then that would be my first function. The outputs are the purples, which are the inputs to this second function, and composition and chain rule and all good, and we can play all sorts of chain rule games. So that's really all we got to do is figure out how to stick a new variable in that one spot. And it's really not that big a deal to do this. I'm going to do that by calling my new variable x1 star. The star there's nothing magic about the star. That's just a notational tweak. The formula for x1 star is that it's x1, right? It's just x1. I mean, I do want it to be x1, right? I just need it to have a different name. Right? Then, when I say, per this equation right here, that I want z1 to be a function of, well, y2 and y1 and x1, yeah, okay, but x1 is the same as x1 star. So I just rewrite it like this. All right, one little tweak, and we're in business. Everything's fine at this point. Now I have, as you see in this adjusted diagram here, I have this is my function I might call f, and this, with the colors. This is my function I might call g. I'm literally composing what goes out of the first, it goes into the second. We're all good. And now you can write down the chain rule. We have 3 intermediate variables, thus giving us 3 terms. Y'all remember how all of that works. 3 intermediate variables, 3 paths through which changes can propagate. Reminder, we're interested in the partial of z1 with respect to x1. So 3 paths from x1 towards z1. And off you go. And I'll just point out the one sort of convenient little lucky break is that, when it comes to the question of what is the partial of x1 star with respect to x1, okay, well, that's a world's easiest partial derivative. It's just 1. Because that's the formula for x1 star. It's literally x1. And lo and behold, now I've got my new chain rule that totally makes sense. Okay, and we're out of time, so it's the perfect stopping point. Y'all have a great weekend. See you later. And don't forget about attendance.